So welcome to the Hangout. As we are waiting for the other people to join from Brazil, let's first go around. I mean, we already had, looks like, a little bit of introduction, but we will still go ahead and introduce ourselves and then start off with the questions, I guess. So let's first start with this CERN LHC control room. Mirko, do you want to introduce yourself?
Yeah, hi, I'm Mirko Boyer. I'm engineer in charge in the CERN control center. Actually, I was on shift this morning. It's a really bad morning, and well, that's it.
Hello. Yeah.
Okay, now going over to the ATLAS control room.
Yeah.
Hello, my name is Stephen Goldfarb, and I'm one of 3,000 physicists working on the ATLAS experiment. This is our control room. You have the point of view here from the shift leader, and so you can take a look at our control room here. Just give you a quick glance. And we're just here ready to go, waiting for those stable beams that we've been promised. And we're ready to start the data.
Oh gosh, you're right. It's my fault.
Soon after the Hangout, right? Hi, so now going over to the CMS control room, David?
Yeah, so I'm Dave Barney. I'm a physicist for the CMS experiment, and I'm here in our control room. I can also show you some of the people on shift behind me. We're also eagerly awaiting these first physics collisions of 2012 that Mirko has promised us, but he's gone back on his promise again. So we're just waiting for him.
Keep waiting, David.
Okay, so while we are waiting for the beam, let's see if we can actually have some discussion. I see that that our Brazilian friends have already logged in. Can everybody there hear me? Can everybody wave your hands to confirm that you can hear me? Yay! Okay, fantastic. Okay, so the way this is going to go now is it will be our Brazilian friends first actually asking 3 questions, and then followed by Lydia asking a question, and then again back to Brazil for 3 more questions, and then a few questions from Don. So let's start with our first question. Can anybody from Brazil actually confirm and say something that they will be asking a question?
I hope they want to ask in English. I don't know. Okay.
We can just about hear you, but you're very quiet.
Yeah.
Hello, can you hear me?
Yes. Can you come a little bit closer to the mic, please?
Hello, can you hear me? Loud?
Yes. A lot better now. Yeah.
Okay. So I'm gonna make my first question. I want to know what's the main difference between ATLAS and CMS, and I want to know if they work in collaboration.
Okay, I think to be fair, I will split this question into 2 parts and let both David and Steve answer this. So David first.
Okay, so I could be politically incorrect and just simply say that CMS is so much better than ATLAS, but oh, I've said that, sorry. So what we do is we have at least 2 experiments trying to look for the same things but built in different ways. And the reason for that is, when you're at school doing an experiment, usually your teacher knows the answer. So you have something to compare your results against. What we do is completely new. We're looking for things that no one has ever seen before, and looking for, well, sometimes we don't even know what we're looking for. So having 2 experiments confirm each other. So if one gets a result and the other one doesn't see the same thing, it's probably not real. Whereas if both experiments see the same thing, you can pretty much be sure that you've seen something real and maybe new physics. So having 2 experiments is a great thing to have. Ideally you'd have even more, but 2's enough for us. And we build things in different ways. So the aims are the same. The overall structure is very similar for these two detectors, but they're built differently, different technologies and so on. Maybe Steve can comment a bit more on that.
Sure. I would mention that perhaps as important as having different technology is the fact that our 3,000 physicists are completely different than the 3,000 physicists working on CMS. And that's extraordinarily important. We provide checks within our own experiments continually. Peer review is probably the most important and powerful tool that we have in science. So we each check our results, and if they survive our own internal reviews, then we compare against each other, and we each review and take a look and see if we measure something that's the same or similar or different. Now, technically, if you look at the two experiments, and I invite you to look at them, take a look on the CMS page, take a look on the ATLAS page, you'll see that they really look different. And the driving difference between the two is how they go about measuring, measuring the different particles and detecting them. What drove the different sizes between the two has to do with the magnets. In fact, our acronyms, the compact muon solenoid, and the ATLAS, which is a toroidal LHC apparatus. The name is due to the magnets, the giant magnets, which surround the detectors and which curve muons so that we can measure their momentum. That's really the driving force behind the change of the shapes. And that changed the shapes and the types of technologies used inside the detector. So yeah, the detectors are very different, yet they're both designed to explore, and that's what we're both doing. I wanted to, before stopping, just to introduce Denis, who's here. So if you want to ask in Portuguese, also a question, Denis helped to make sure that the school in Brazil could join.
Does that answer your question?
Fantastic. So yeah, I guess we all work together in a way that we always cross-check each other. So going on to the second question.
Thank you for the answer.
So who will be asking the second question?
Hi, my name is Laura.
Hi, Laura. Can you also please stay a little bit closer to the mic? We can almost hear you.
I'd like to ask why the detector must be so big?
Okay. Why the detector must be so big? Again, I think this question can be split between Steve and David. Maybe Steve want to go first this time?
Okay, I think maybe I should. we have well, in volume, ATLAS has the largest of the experiments. In weight, CMS is twice as massive as ours. And there's a very good reason for it. As I mentioned, the magnets that surround the detectors have a different shape, and that drives the size. The reason they have to be so big is because we're exploring. It's almost the same reason why telescopes got longer for us to see further out into space. In this case, we're trying to look at particles
on the other side
which are more massive. And when a more massive particle, those are the ones we haven't found yet, when a more massive particle decays, the particles that come off of it, when it disappears, it shoots off particles, and those are going to go very fast. They're going to have a lot of energy. The way we can measure the momentum or the energy of a particle that's charged is by curving it. We do that with strong magnetic fields, and the bigger volume you have to measure that curvature, the more precise your measurement is. As an example, I think both of our detectors in the tracking parts get down to measuring microns of precision, and that's over something for ATLAS we're 46 meters in length. So if you can measure precisions on the order of microns over half of a football pitch, then you can tell one of the new fast-moving particles you can measure its momentum. So it's necessary to be large to do that. Maybe Dave has a good explanation as well.
I think you covered it pretty well, actually, Steve. I mean, we don't just build the biggest objects we can make for fun. I mean, they're necessarily large, they're necessarily huge, because of the huge energies of the collisions that are involved that our friends from LHC are providing us. So the particles that fly out are higher energy, higher momentum, travelling faster than anything that's ever been produced in the lab before. So the experiments that Steve and I work on are the biggest experiments of their type ever made, in fact. But they have to be like that.
Maybe Mirko can add why the LHC has to be so big too, just to make it complete.
Wow, good question. Okay, let's say like that. If you want to increase the energy of the particles that you are smashing one against the other, you have two ways of doing that. Well, essentially for the part of acceleration, it's just the RF part which provides the energy. But if you want to keep the particles in the same circumference all over this activity of acceleration, this process of acceleration, you have either to increase the diameter of the particle, because as long as you if you increase the energy of the particles, they tend to be bent less if you keep the magnetic field that made them to turn in a circle constant. So you will have to increase the diameter of your machine, or if you want to keep them confined in the same machine, you have to increase the magnetic field. Let's say the size of the LHC was done such that at the moment where the LHC tunnel, that was indeed the lab tunnel, well, the tunnel where the previous accelerator was installed, was chosen so that with the maximum magnetic field which we could provide at the time, we could generate at the time with traditional magnets, we had the maximum energy with a reasonable small machine. I don't know whether the explanation was complicated, whether you got part of it totally.
Right. So yeah, we really need very high energy particles, and we need very big machines to actually be able to detect them as precisely as possible.
The ideal machine would be a 1,000 kilometer in circumference with the highest possible magnetic field, but of course both options goes against the. I mean, both options need, of course, a lot of money to be used for building them.
Okay, thank you very much. Thanks to all the three experts. So, should we go on to the next question?
Does the detector break down?
Maybe this one we will start with Mirko. The question is, does the detector break down?
Well, it's not me the right person to answer this question. I have in mind a clear episode when part of the detector broke down actually. It was a cooling element of CMS. Because of that, we have to stop the.
Hey. No saying bad things about CMS. Come on.
No, I mean, I must say that both the machine and the experiments are at the top of technology. They are very, very complicated elements. We have 27 kilometers actually of very high technology components. So, of course, from time to time they break down. It happens for the LHC quite often because we have more than 26 kilometers of magnets, electrical components, and so on. Of course, the experiments being less big in dimension, they are enormous, but compared to the LHC, they are small. Of course, the breakdown rate is of course low. I don't know, Dave, whether they won't come.
Yeah, I can comment a little bit there. There's a big difference between the experiments and the LHC. What we have built for CMS, for example, is this enormous cylindrical object that has many layers. So it's a bit like a cylindrical onion, if you like. And each layer does something different. But actually accessing the inner layers of this detector is really very difficult. So sometimes things do break. So they break really on the inside. But we have no way actually to access this. We have no way to fix these problems when they occur. So then we have to leave it. So of course we don't like that situation. So the way we build our detector is with what we call redundancy. So we have many layers doing similar things. So if one part breaks down, you've got the next layers that can take over the job. So even if some parts are not working, you can live with the rest. At the moment in CMS, for example, we have about 99% of our detector is actually fully operational. And that's pretty good for something as big and as amazingly complex as CMS. But of course, you know, things always do happen, but hopefully not too often.
Well, if I can make a comment for ATLAS, well, in the same way as CMS, so it's a huge detector, so the electronics that you have is quite complex, and the electronics that is exposed to a huge amount of radiation, so when you have the particles colliding, you have a lot of flux of particles, and these of course damages the electronics. So you can, I can just to quote a few numbers, we have 200,000 about 200,000 cells on our calorimeter, millions of pixels to be read out. I don't even know the number correctly, actually, it's a huge number. But the point is that it's a lot of electronics which is connected to the detector directly. So I can give you, for example, an example actually of the case for some parts of the detector that sometimes we have issues, like we have power supplies, for example, which sometimes may fail. And this, of course, is quite bad for ATLAS. So what we do is we do exactly as the CMS colleague just said. We have redundancy. So there are other pieces that take the job and don't let the detector stop working. But it's true that, for example, during shutdowns, it's not very easy to go into the detector, but eventually we can, in some parts of the detector, we can go. And for example, this beginning of this end of last year, beginning of this year, during the shutdown period, I was actually downstairs changing pieces. So we do that from time to time. Well, we can only do that, of course, in the end of the year because we have to survive the full year doing data taking. We should not stop the data taking. But at some point, we might just want to, well, when we have the stop for winter shutdown, so Christmas and so on, some people do not have Christmas, and some people go down the detector and try to exchange a few of the pieces that are not so good as the other ones. So this happens a lot, and we have to have one safety thing, which is to have redundancy. The other safety thing is to be able to, at the end of the year, go there and put the best pieces in place.
Right. And also I can assure you that there are a lot of physicists who have sleepless nights when you turn the detector on and off. So, okay, that was thanks again to all the experts, and also thanks to the questions. Now I think I will ask Lydia to ask the next question.
Okay. So my question is it possible that there is particles that are so massive that you're not going to find even at high energies, like, I don't know if it was 14 teravolts or something like that?
Yeah, that's a very good question. I mean, right now we are not running at 14 TeV, we are running at 8 TeV. So yes, I think maybe we will start with CMS.
Yeah, I mean, there are many theories around about different particles that may exist to explain one phenomena in the universe or another. Some of them are relatively light, like the Higgs boson, if it exists, is relatively light, and we should find it this year. And even ATLAS might find it this year, which would be amazing. But then there are other types of particles that are, for example, heavy versions of some things that are familiar to us, like the Z boson. There might be a heavy version of the Z, which could give us indications of extra dimensions or many other types of theory. And they may be much heavier, 1 to 2 TeV, for example. So the LHC could definitely find those as well. But there may be even other theories that postulate much higher and much higher mass particles, that clearly the LHC has a limitation, and we won't reach those. I don't actually know what those theories might be, actually, that postulate even heavier things. So maybe Steve, my all-knowing partner on the other side of the ring, knows this.
Well, I wouldn't know, but what I would say is that I would give you an idea of the accounting that we have so far. So I'll give you our ignorance factor. What we know by looking out at galaxies is that given the particles we know and that we have been able to measure, we can account for about 20% of the mass that would be necessary to hold them together. So we're certainly missing a lot. And whether that's due to a particle that we might detect later on this year even, or whether it's due to a whole variety of different particles, we don't know. Since we haven't been able to detect it so far, there's a good chance that even with the LHC we'll miss it. And by the way, these particles which we haven't yet detected, the way we look for them is by noting that there's an imbalance of energy when we have a collision, and that something snuck out of our detector without us detecting it. Statistically, we take a look at that and we will be able to say something. But it's kind of interesting to know that one of the 80% of what's out there could be something that we only see by noticing that we don't see it.
Right. Fantastic. So yes, there are a lot of exciting stuff that we still have to detect, and we will look forward to it. So given that we only have 5 more minutes left for this hangout, I will ask Don to ask his question before we go back to Basil again.
Thanks very much. So my question is around the data and the way you handle your data processing. One thing that puzzles me is the sheer amount of data that you collect through your experiments. If you could share with us a little bit more about how you handle the data collection, storage, processing. Do you consider your data analysis methods and algorithms to be effective? And how long do you store all the raw scientific data do you collect? Do you at any point dispose of it? Are there any potential risks in doing so?
Right, that's actually a very interesting and an important question that a lot of computer scientists are also involved in trying to maintain our data. So I will first go to Atlas to understand their model, and then maybe David can give a short summary of the CMS model and how we do it. They're more or less similar, but there are slight differences.
Well, okay, so unfortunately, we did not start to take data now, but if we had started, you would see that we can record up to 300, 400 events per second, and each event is more or less 1.6 megabytes. So if you start to count everything, you're going to see that you're filling a regular CD every 2 seconds. So the amount of data is really huge. And the amount of data that you take per year, you can guess it's really huge amount that we have to not only store it somewhere, and to maybe answer part of your question, we don't throw away, we don't want to throw away for as long as we can, at least. So far I don't think there's any plan of throwing away physics data, not at all. But in order to also handle this data and try to extract physics, we also know that CERN, even though we have a computer facility which I think has now more than 20,000 computers running there, this computer facility is not even close to what is necessary to fully process and find things like the Higgs or whatever we're going to find during the next year or so. So the way that we have in order to be able to really deal with this data is to spread data around all the world. So actually you have 11 data computing centers, I think it's 11, right? 11 tier 1s that they are called, as they are called, for Atlas, spread all over the world. So there is one in United States, one in Italy, one in Germany, I think one in France, and so on. And we spread the data, and we also spread the task. So the task must be handled at each place where the data is. And so then, okay, if you want to find a new particle or do an exercise with all the data, you have to make sure that whatever you're going to do can be run all over the world at once. in such a way that at the end you just get a small amount of data that represents your result, that tells you, that there it is, there is the Higgs boson, there is whatever your supersymmetric stuff and so on. So that's the way that you have to make sure that you can run this in distributed mode and then afterwards recover the data. Then, well, I don't know if I mentioned the name grid. This is what we call grid computing.
Okay, yeah. So that's, yeah, thank you for the insight, and I think David can add a little bit more on how different is the CMS model.
I mean, the CMS model is essentially the same, but I just wanted to go back a step to one of the parts of the question you asked about, do we throw away data? In fact, we throw away 99.999% of our data. Wow. Let me show you. Let's see if you can see this. So actually on one of the screens behind me, there's a display of our data acquisition system, but I'll bring it close to you. Let's see if you can see this. Not very well. So there's a number in there that's backwards, which is really helpful to you, which shows that at the moment we're taking about 80,000 events, or having the equivalent of 80,000 collisions every second. Now, of course, they're not real collisions at the moment. We're still waiting for our LHC guys to do their job. One more dig at Mirko. But we're running at a very high rate. And what this rate is, it's we have all of these collisions happening all the time. So we have about millions at the moment. I think it's going to be around 20 million collisions happening every second, or 20 million crossings of protons every second. And we have to take a very quick decision on which ones are actually of interest to us. And as Steve and his colleague has said, we can only actually store a handful of those, like 200 to 300 of those collisions can we actually store every second. So most of the data we have to throw away. The number I showed you, the 80,000, is what's left after we've made like a first decision. We look at some basic characteristics of the data very quickly and try and understand whether it's interesting or not. Of course, we have to be very sure that we take the right data and don't throw away all the good stuff.
So you have an educated guess in the process, right? You decide which streams to ignore and which ones to record, to save.
Yeah, I mean, it's like, you know, imagine you get all the newspapers in the world for a certain day, and somewhere in there there's a story that you really want. So the first thing you do is you know some basic things. You know the story might be in Portuguese, let's say. So the first thing you do is you throw away all of the newspapers that aren't in Portuguese. So you'd make a very brief, very quick decision at a very basic level. You keep something, and now you look through all the Portuguese language newspapers, and you look at the headlines. So that's your next step of filtering, if you like. And then finally you look at the headlines that actually concern you and go through those stories in detail. So we have these different levels that are very similar to that in CMS and ATLAS. We make a quick decision on very basic things, keep some large fraction of the data, have a look at in more detail, and then only keep a few hundred at the end of it.
Right, so the technological bottleneck... Sorry, go ahead.
If I may add something, because I have the impression from what they say that we provide you crap collisions with the product, which is not the case.
No,
we provide very good, very energetic, very dense beams,
perfect.
But otherwise, I would say we could work only a few minutes a day instead of being around the clock all the days of for 10 months. So we have very good quality beams, but of course your choice is to I would say it's essentially your choice to decide and keep only a very small percentage of the collisions, taking only the extremely good collisions that we'll have in the machine.
Yep. Maybe if I can add, do we have enough time to add a comment?
Sure. Yeah, we're going to extend this hangout till 60-40, but I do have a question for Mirko before we leave, so I think we have 2 minutes more for comments, yes.
Okay, so let me just add this comment just to make sure it's clear about what we throw out and what we keep. The vast majority of these wonderful, incredible collisions that we get from the LHC,
thanks, Steve. I appreciate it a lot.
regardless of how well they are, a lot of the times when the protons come together, there's just a little scattering that happens, and that's the kind of physics that we've already studied before. So the vast majority of the stuff that we're throwing out are things that we already understand. It's not that we're just really being very picky about what we keep. We have some, what we call in our trigger of our selections, we call it a trigger menu. We have different items that we want to keep. We include in there some which are pretty general. They just say we want to see that there are some hard jets coming out, that there's been a strong interaction. And so we aren't necessarily specifically only looking for Higgs or SUSY or these things. We also keep channels open for anything that's new. And we have a good idea from the past what that can look like.
Yeah. And also, I think just to finish this discussion, there's also an issue about what we do with this data once we have recorded it and analyzed it for the first round. And that actually is much more a complicated question, and I think this is something both the experiments are still trying to decide on what to do with the data in the very long run. Of course, it will be kept, and of course it will be kept in a way that it can be used or looked at again. But exactly what would be done with it is still being discussed, I guess. I mean, if I'm wrong, David or Steve can correct me.
Just one sentence, quick sentence. Our LHC colleagues, they really produce wonderful collisions. It's not their fault that we don't have all the collisions that are interesting. It's nature's fault at the end that do not produce for all the collisions produce a new Higgs boson, for example, and then we could go home in 5 minutes.
Yeah, actually what he's saying there is he's trying to make it so that Mirko provides better collisions to ATLAS than to CMS.
I got that, don't worry, got that.
So now now I have a question for Mirko about now that we have the expert here. So what is going on at LHC control room right now? What will happen later tonight?
Yeah.
Maybe a little insight would be great. Yeah.
Yeah, sure. Well, the aim of today was getting the first stable beams collisions. That is essentially going up with 3 bunches on each beam, 3 packets of particles on each beam, up to 4 TeV, squeezing them down in the experiments and then having them collide in the experiments and declaring what we call stable beams, which is a phase where we don't touch the beams and the experiments can switch on all the components and detecting. Let's say measuring all the events from these collisions. Unfortunately, we've accumulated some delay due to some problem in the machine, and also Dave, just continuing on the history of faults on the detectors, I read in page 1 that we have problems with the CMS BCM at the moment. Can you confirm that? Yes, actually. Also, not only the machine, but also the experiment broke down.
Yeah. So in fact, my colleague behind me is currently working on exactly that. Yeah. And it looks like to be a power supply problem.
Yeah. Well, by the way, we are joking, of course. We are all working the same objective. We want to accumulate the maximum possible number of data by the end of this year. What we aim at doing. Are you there?
Yes.
Okay. I saw the blank screen.
I think we lost Lydia.
Yeah.
Yeah. What we are doing now is essentially doing some of the very last verifications before having what I called before stable beams. So hopefully by the late afternoon, beginning of the evening, we should be able to deliver stable beams to the experiments, and I hope both David and Steve will be happy about that.
Yes.
Okay. Fantastic. Thank you. Yep, I bet ATLAS and CMS and all the other experiments are also quite looking forward to this. And so this, I think, concludes our first session of the Hangout. I will send you another invite within the next 5 minutes to start with another Hangout. I think our Brazilian friends are actually going to join us back and ask us more questions for the next Hangout. So thank you all again for very nice questions and very nice discussions. And I'll see some of you back again in a couple
Can we just say one last thing? I mean, if you want to send us more questions, we'll try and respond by email as well.
Of course.
That is true.
Yeah, absolutely. You can send comments on our Google Plus pages, I believe.
Yeah.
Great. Thank you.
Okay.
Thanks very much.
Thank you for all the great questions. Thanks,
Thanks
everyone.
a lot. Yeah.
Thank you. Bye.
Bye.